Hey everyone, welcome. Let's get completely dialed in right off the bat. Today, we're setting a really focused, dark-themed academic atmosphere for this standalone masterclass explainer. We are going to completely unpack object-oriented programming, or OOP, with Java, specifically focusing on Unit 1. Whether you're aiming to build massive enterprise applications, dive into Android development, or honestly, just master the foundational concepts of computer science, you are exactly in the right place. Okay, let's dive into this.
Here's the roadmap for today's explainer. We're going to start with the introduction and history of Java, and then move right into its key features. From there, we'll demystify the Java environment by understanding the JVM, JRE, and JDK. Next, we'll get our hands dirty with Java's syntax and basics, followed by operators and control flow. And finally, we'll culminate with the absolute bedrock of the language, core OOP principles. We are not skipping any foundational concepts today. All right, let's kick things off with our first topic. Introduction and history. To truly master Java, we first need to understand its origins. Why? Because the exact problems it was created to solve back then are the very reasons it remains so incredibly powerful today. Let's step back to 1991. A team at Sun Microsystems known as the Green Team, led by James Gosling, who's widely considered the father of Java, started a project initially called Oak. And what's truly fascinating is their original intent. They were actually trying to design a language for interactive television. But, well, it turned out to be way too advanced for the digital cable industry at the time. The market just wasn't ready for it. However, the internet was just starting to emerge. By 1995, the name Oak was already a registered trademark for another company, so they renamed it to Java. It was actually inspired by the Indonesian coffee the team drank constantly, which, if you've ever wondered, is exactly why the logo is a steaming cup of coffee. After the JDK 1.0 launched in 1996, the language just exploded. Fast forward a bit, it was acquired by Oracle in 2010, saw massive functional programming updates in Java 8 in 2014, and today, in 2024, it seamlessly integrates with cutting-edge cloud and IoT technologies. Moving right along to our next core topic, key features of Java. So, why did Java survive when so many other programming languages just kind of faded away? Let's look at the intrinsic qualities that made it an absolute industry standard. These are what we call the Java buzzwords. First up, it's strictly object-oriented. Essentially, everything is modeled as an object. Second, and this is absolutely crucial, it is platform-independent. It follows the famous write once, run anywhere, or WORA philosophy. You see, unlike C or C++, which compile down to machine-specific code, Java compiles to bytecode. It's also simple and secure. It intentionally stripped out complex C++ features like explicit pointers. That means programmers can't directly access unauthorized memory, which prevents a whole host of system-level crashes and security exploits. Plus, it runs your code safely inside a secure sandbox. Next, it's robust, boasting incredibly strong memory management and error handling. And finally, it's multithreaded, which allows multiple tasks to run simultaneously and distributed, meaning it was designed from the ground up for network-level applications. Okay, Section 3, Understanding JVM, JRE, JDK. We're going to peel back the layers of Java's architecture right now, moving from the tools you type your code into all the way down to the internal engine actually running it. Think of Java's architecture as operating in concentric layers. At the very core, you have the JVM, the Java Virtual Machine. Enclosing that is the JRE, the Java Runtime Environment, which basically adds the Java class library to the JVM. And then, enclosing everything, is the JDK, the Java Development Kit. So the really crucial takeaway here is this simple equation. The JDK equals the JRE plus your development tools. If you're an end user and you just want to play a Java-based game, you only need that middle layer, the JRE, to run it. But if you're a developer actually writing code, you absolutely need that outer layer, the JDK, because it includes your compilers and debuggers. Now, let's trace the actual journey of your code. You start out by writing human-readable code in a .java file. You pass that through the JVC compiler, which is one of those tools from the JDK we just mentioned. Now here's the kicker. This compiler doesn't create a Windows executable or a Mac application. It creates a .class file containing bytecode. This is the absolute magic of Java. You can take this exact same bytecode file and hand it to a Windows JVM, a Linux JVM, or a Mac JVM. The bytecode itself is platform independent, but the JVM acting as the translator, that part is platform dependent.
So what exactly is happening inside that JVM? It's essentially a three-step internal process.
First, the class loader subsystem brings your compiled.class files into memory. Second, memory allocation happens. The JVM divides its memory into specific areas, primarily the heap, which is where objects live, and the stack, which is where local variables and method executions are kept track of. Finally, the execution engine takes over. And what's really interesting here is the JIT, or just-in-time compiler. Instead of reading bytecode line by line, which can be pretty slow, the JIT compiler identifies frequently used chunks of code and compiles them down to native machine code on the fly during runtime. It's a massive performance boost.
Up next, Java syntax and basics. We've covered the theoretical architecture, so now let's transition to some applied coding and take a look at the actual structure of the language.
Let's break down the classic Hello World program. A Java source file follows some very strict conventions. First, notice the class declaration, class Hello World. A strict rule in Java is that if a class is public, the file name absolutely must match the class name. So this file has to be saved as helloworld.java. Inside that class, we have public static void main and then string args in brackets. This is the entry point of every single Java application. Public means it's accessible from anywhere. Static means the JVM can call this method without having to instantiate an object of the class first. Void simply means it returns nothing. String args allows the program to accept command line arguments. And inside all of that, system.out.println is our standard command to push text, in this case, hello world, straight out to the console.
Now, Java is a statically typed language. That means you have to declare variables type before you can even use it. Looking at the data hierarchy, we have two main branches, primitive and non-primitive. There are exactly 8 primitive data types. You've got your integers, byte, which takes up just 1 byte of memory, short, which is 2, int, which is 4, and long, which takes 8 bytes. For decimals, we use floating point types, float, and double. And for our non-numerics, we have char for single characters and boolean for simple true or false values. Non-primitives are your more complex things like strings, arrays, and classes, which we'll explore more shortly. Depending on exactly where you declare these data types, they behave completely differently in memory. We're looking at 3 types of variables here. First, a local variable is defined inside a method, like our main method. Because it's local, it lives in the stack memory and is immediately destroyed the second the method finishes. Then we have an instance variable. This is defined inside the class, but outside of any specific method. It belongs to a specific object and is stored over in the heap memory. Finally, we have a static variable, marked with the static keyword. This one belongs to the class itself, not any individual object, and it's stored in a special place called the method area. Understanding this scope is absolutely critical for good memory management.
Let's move on to operators and control flow. Now that we have variables sitting in memory, how do we actually manipulate them and make our programs do work?
Let's see some of these operators in action. Your arithmetic operators are just standard math, plus, minus, modulo. But look closely at the unary section. When you see a++, that's a post increment. The program uses the current value of a and then adds 1 to it. But ++a is a pre-increment. It adds 1 before using the value. It's a subtle but huge difference. Down in the shift section, we have 10 left shift 2. A left shift operation effectively multiplies the number by 2 raised to the power of that right operand. So take 10, multiply it by 2 squared, which is 4, and we get 40. It's a really clever, high-performance way to do math right at the binary level.
Beyond just manipulating data, we need control flow. Here's a selection statement known as the switch case. It is a much cleaner alternative to writing a massive, ugly wall of if-else statements. You pass in a variable, say day equals 2. The program jumps directly to case 2 and prints 2 for Tuesday. But here is the absolutely crucial detail, the break keyword. If you forget to include break, Java will experience what's called a fall through. It will just keep executing the code below it, hitting default and printing invalid, even though your case matched perfectly. You have to explicitly tell the switch statement to break out. When we need to execute code repeatedly, we use iteration, like a while loop. Let's look at one used to reverse a number. This is an entry-controlled loop. The condition, n is not equal to 0, is checked before we even enter the block. Let's walk through the math together. If n is 123, well, 123 modulo 10 gives us 3. So our rev variable becomes 3. Then we divide n by 10, shrinking it down to 12. On the next pass, 12 modulo 10 is 2. We multiply our previous rev of 3 by 10 to get 30, add the 2, and now rev is 32. See how we're shifting the digits? This loop just keeps spinning until n hits 0. It beautifully demonstrates how logical conditions completely control execution flow. All right, Section 6, Core OOP Principles. We have officially arrived at the capstone of Unit 1. This is where we take all that syntax, memory, and logic and tie it perfectly into Java's fundamental architectural philosophy.
The entire heart of object-oriented programming relies on understanding the difference between a class and an object. Think of a class as a blueprint for a building. It's just a template. It defines how many doors and windows there should be, but you can't physically walk inside a blueprint. An object, on the other hand, is the actual physical building created from that blueprint. It's a real-world instance that occupies actual space in memory. You can use one single blueprint to create 100 different buildings, just as you can use one class to instantiate 100 different objects.
And governing all these classes and objects are the 4 pillars of OOP. These exist to reduce code complexity and maximize reusability. Pillar 1 is abstraction. This is all about hiding complex internal mechanics and only showing the essential features. When you drive a car, you use the steering wheel and the gas pedal. You don't need to know the exact physics of the fuel injection system. Pillar 2 is encapsulation. This binds your data and the methods that manipulate that data into a single sealed unit. Just like a medical capsule hides its internal ingredients, encapsulation protects your data from unwanted outside interference. Pillar 3 is inheritance. This allows a brand new class to inherit properties from an existing parent class, much like a child inherits genetic traits, which saves us from rewriting code. And finally, polymorphism, which literally means one name, many forms. This allows a single method to behave differently depending on its context. For example, a single method named draw could trigger completely different code depending on whether you're asking it to draw a circle or a square. We have covered some truly incredible ground today. We traced Java's history, unpacked the layers of the JVM architecture, parsed through strict syntaxes, and mapped out the 4 essential pillars of OOP. So I'm going to leave you with this final thought. By understanding these isolated blueprints, these variables, and the giant compiler that runs them, how do we begin to interlock these individual objects to architect massive, highly scalable, real-world software systems? I want you to keep that in mind as you process all this material, and I will see you in Unit 2.